Hey there, students. So we are now going to take a look at 7.3, the last section that we're going to cover from Chapter 7. And in Chapter 7, we've been estimating parameters and determining sample sizes. And in the first section, we were looking at the population proportion, and we created confidence intervals for that. And then we looked at how to create a confidence interval for the population mean. And in the final section, we're going to do the same thing for standard deviation, or variance, which is the square of the standard deviation. And so I'm not going to spend as much time or go into any detail in discussing what a confidence interval is or exactly how it's created, since we spent quite a bit of time on that on the first two sections. And I'm just going to focus on how we do things a little differently and what's different when we are instead trying to estimate the standard deviation for the population, or the sigma value. And again, we are not covering 7.4. All right, so key concept. This section presents methods for using a sample standard deviation, which is the S symbol, or sample variance if you were to square that, to estimate the value of the corresponding population standard deviation, sigma, or sigma squared if you're talking about the variance. And here are the main concepts. As before, what we saw with proportions and means, you can make a point estimate. The sample variance is the best point estimate for the population variance. So notice they're talking about the variance instead of the S value itself. And when we are trying to make estimations for the population, we need to do our statistical work using the variance, because as you may recall from earlier chapters, a standard deviation values of samples do not actually target the standard deviation of a population. In order to get better targeting, to have the results be better, we need to use the variance instead. And so that's one key difference about the statistics we're going to do in 7.3 compared to the first two sections, is if you were trying to estimate with a point estimate of the population proportion, you just used your sample proportion. If you wanted to do the population proportion, the population mean, you would just use your sample mean. But instead, when you want to make an estimate of the population standard deviation, what you do is you look at the variance of your sample, and then that gives you a variance prediction for the population. And this will be very important when we get to the confidence interval, when we're creating a confidence interval about standard deviation, but we're doing our statistics using variance. So I will demonstrate that with a problem as well. When we can use a point estimate by focusing on the variance. As we did before, we're going to want to be able to construct a confidence interval. So when constructing a confidence interval estimate for a population's standard deviation, meaning we would have an interval or range of values, and we would say that we have a confidence level, like 90% or 95% or 99% confidence, that the interval of values we're providing contains the actual standard deviation of the population. So that all works logically the same way it did for proportion or mean. However, it says in order to come up with that confidence interval, we construct a confidence interval using and there's a big X with a little square symbol on it. That's called the chi-squared distribution. So the chi-squared distribution, and think of the little square also reminding you that you're using variance instead of the actual standard deviation. So we will actually construct a confidence interval about the variance and then just adjust that by taking the square root to get a confidence interval about the standard deviation. So the little 2 there as a power on the big X for the chi-squared, the squared part reminds you that this is the square of the standard deviation, which is variance. So this is really the variance distribution, or the distribution we use for variance, because of the fact that we have to do it for variance instead of standard deviation. All right, so other than that, we're doing kind of the same things here. And so if we look at this, they're going to give us a formula. So before, we have formula for how to calculate a z-score, and we had a formula for how to calculate a t-score for a t-distribution. So this would be a formula for how to calculate the chi-squared score. So the chi-squared distribution will have a chi-squared score. It'll have chi-squared critical values, things like that. But as usual, we're going to de-emphasize the formula use and do those calculations using StatCrunch. But nonetheless, we want to understand that the chi-squared distribution, the chi-squared score, is like a t-score or a z-score that you might see in one of our earlier distributions. So in specifics, just to see what it says here, in a normally distributed population with a variance of sigma squared, if we randomly select independent samples of size n, and for each sample compute the sample variance, s squared, then the sample statistic, which is based on this distribution, it's like a z-score or a t-score, has a distribution called the chi-squared distribution. So notice everything in the description is about variance. None of it is directly about the standard deviation. Okay, well, like we had with the t-distribution, the size of your sample matters and comes into play in the distribution shape itself. And so we define this degrees of freedom, and just like with the t-distribution, the degrees of freedom is 1 less than the sample size. And you may recall that the t-distribution varied slightly in its graph based on the degrees of freedom. And the larger the degrees of freedom, the more and more the t-distribution looked like a standard normal distribution. So a similar thing will happen, and we can look at this graphically for a chi-squared distribution. A chi-squared distribution will look more and more like a normal distribution the higher the sample size and the higher the degrees of freedom. But nonetheless, think of it like you did for your t-distributions in 7.2, that you need to work with the degrees of freedom. So here is what our graph looks like. And so here's how things for the chi-square distribution are more different than they were for a normal distribution or for a t-distribution. Because a chi-square distribution is skewed to the right. So that means we lose the properties of symmetry that we had with the normal distribution. And if you imagine, you're still going to have a situation where you're thinking about the mean value being sort of the most likely or expected value here under the middle of the big bump. However, notice since it's not symmetric, if you are coming up with a confidence interval, the confidence interval will not be equally distributed on the right and left sides of the mean value. Because the curve is not the same on the right and the left sides of the mean value. It's not symmetric. So you can no longer describe a confidence interval by giving some like S value and then saying plus or minus E. You have to just give the lower end and the upper end of the confidence interval, and of course StatCrunch will do that for us. But anyway, so it looks a little different. Also notice that unlike the T and the Z distributions where the mean value was 0 for those normal curves, here the extreme value on the left is 0. All of the chi-squared values on the chi-squared distribution will be greater than 0. And then they head off to the right, get bigger and bigger and bigger. So you will never have like negative and positive critical values like from -2 to +2 on a z-score or on a t-score, it'll always be between two, a lower and an upper, but both positive, two positive chi-squared critical values. Anyway, so some changes here. The ideas are the same, but because of the nature of a variance distribution, we don't have a nice symmetric standard-looking normal distribution. Well, let me read off the top. The chi-square distribution is skewed to the right, unlike the normal and student t distributions. The values of the chi-squared can be 0 or positive, but they cannot be negative. You can see from the scale of the graph that the starting point is 0. And again, chi-squared standard deviation measures how far apart the data is spread. So you can kind of remember before that standard deviations are never below 0. So this sort of makes sense because we are now imagining distributions. So if I take values for standard deviations that were never below 0, and then I square them to get variance values, those will still be never below 0. And then if I distribute all those possible results, I should get things that are never below 0. So keep in mind, this is about standard deviation. And the standard deviation itself could only equal 0 when all the data values were exactly the same. So that's what the 0 bottom value on the end represents, is that the entire data set, all the data values were exactly the same. And if that's the case, then the standard deviation and the variance is 0 because there is no variance in the data values. So that's the extreme low end, and then as soon as the data values are different from each other in any way, then you start to get standard deviation and variance values to the right of 0, getting positive values. All right, and so here they're showing how the curve changes based on the degrees of freedom. We saw a similar kind of graph like this in the slides for the t distribution. But with the t distribution, it stayed symmetric and the lump was perfectly in the middle. It wasn't skewed, and it just kind of was rising up to look more like a normal distribution. Well, a normal distribution would have more symmetry and less skewing to the right. And what you can see from this graph with degrees of freedom equal to 10 compared to degrees of freedom equal to 20, that as the degrees of freedom increases, the lump moves away from being so drastically right skewed and looks to be a little bit more symmetric. And so the higher the degrees of freedom, the higher your sample size, the more the chi-square distribution starts to look a little bit more like a standard normal distribution. Bigger the sample, the better the results. That's always the case in all of our statistics work. More data, better values. So then they talk about the idea of getting a confidence interval using this chi-square distribution and how it's different. It says because the chi-square distribution is not symmetric, a confidence interval estimate does not fit a format of taking some sample value and adding and subtracting a margin of error. Because we don't have a margin of error that's symmetric with respect to the sample value. So we must do separate calculations for the upper and lower confidence interval limits. And those are just separate calculations. And of course, with a new distribution, they offer us a new table to use, but we're not going to use tables A2, A3, or A4 for finding critical values. We're just going to do that in the StatCrunch. So they talk about when you're looking these thumbs up, and we'll see this graphically, even if we're using the calculating tool in StatCrunch to do the work so we don't have to use the table, you'll have area to the right of a particular critical value or area to the left of a particular critical value. And if you're creating a confidence interval, say at 95%, then the alpha value of 5% is split evenly to those right and left tails outside of the confidence interval range, and that's how you get your critical values. So all of that is similar to the way it was before. We just lose the aspect of symmetry when it's right skewed. So here they're going to have a sample. We'll walk through a sample, but then after this, I'm probably going to go ahead and hop over to look at a problem in StatCrunch. And then also on our Canvas site, in our StatCrunch tutorial videos, I did shoot a video posted there already I think, how to do number 40 on the homework, and I plan today to, at the end of this slide demonstration, to do a different problem on the homework. So you have a couple ways to look at using StatCrunch to do estimating standard deviation problems from 7.3. So it says a simple random sample of 22 IQ scores is obtained. Construction of a confidence interval for the population standard deviation S requires the left and right critical values of chi-squared corresponding to a confidence level of 95% and a sample size of 22. So they're introducing this symbol here, these symbols which you may show up in homework problems. It says find chi-squared sub L, the critical value of chi-squared separating an area of 2.5% on the left tail. So the L is for the left end of the critical value, of the confidence interval critical value. And find chi-squared sub R, the critical value of chi-squared separating an area of 2.5% on the right tail. So if you want 95% interval, you find where there's 2.5% on the right and where there's 2.5% on the left. And then when you go in between those 2.5%, you get the 95% that's in the middle. So that's hopefully similar to critical values that we did for normal and student t distributions. So they show a nice picture. So apparently with a degrees of freedom of 21, they have a little df of 21 here because sample size was 22. Notice that it's a little bit skewed to the right, but it's starting to look a little bit more like a normal curve, not as lopsidedly shifted with the bump over to the left. The skewing to the right is a little weaker. And so the way we get a 95% confidence interval is we find the critical values, which would be the chi-square distribution scores, where there's 2.5% of the area to the right of the right end of the interval, and 2.5% of the area to the left of the left end of the interval. Then there'll be 95% in between. And so they looked those up on the table, and we could use the chi-squared calculator, which I illustrated how to do in problem 40. We can use the chi-squared calculator to find critical values instead of looking it up on the table. So they first recognize that the degrees of freedom would be 21, because you need to know that looking it up on the table or putting that into the calculator. And then they just focus on how they got this area to the right, and they got this critical value of a chi-squared score of 35.479. So at that chi-squared score, there's 2.5% of the area to the right. And obviously, similarly to the left, with a chi-squared score of 10.283, there's only 2.5% of the data to the left. That means between those two critical values, there'll be a 95% confidence interval. So then they would convert those, and now it says to construct a confidence interval. They would convert those values, here is our fun. They would convert those values into values for the variance, which they're showing here with a formula. Again, we're not going to use the formula, but I'm going to illustrate something here nonetheless. So you would use that right critical value, the left critical value that they're showing here. And then, even though it looks like the left one should be, this might be switched. But notice they then took the square root, because everything was done in terms of the variance. And so that to get the confidence interval in terms of the standard deviation, you would have to square root the results you got using the variance calculator to then see what the results would be for the standard deviation. And so we'll have to do that even when we're doing our problems in StatCrunch. Okay, so then they have a round-off rule. Anyway, I'm going to stop the slideshow here, and I'm going to switch over and look at what it looks like to do this in a homework problem. Okay, so it looks like I've set up number 45 here, and as I mentioned, you can also find number 40. I shot a video of that as well, which is already on Canvas. So it says in number 45, this is from 7.3 on homework number 9, listed below are speeds in miles per hour measured from traffic on a busy highway. This simple random sample, you need a simple random sample, was obtained at 3:30 p.m. on a Wednesday. Use the sample data to construct a 90% confidence interval estimate of the population's standard deviation. So they give us the data in this case. So they also give us a link so that we could look up on the table, the chi-square distribution table. So if you look at the table, it's a pain in the butt to use. You have to find your confidence interval size. You have to look for the degrees of freedom. It's a pain. We're just going to do it in StatCrunch. But nonetheless, they give you a link to that there in case you wanted to try using the table. All right, so it says it just asks us what is the confidence interval, or tells us to give it. And we have a left value for the standard deviation, and we have a right value for the standard deviation of the population. So they don't summarize this. They don't tell us what the standard deviation of our sample was or anything like that. They just give us the data. So I'm going to open the data in StatCrunch. And so it's not a big data set, but once it's in StatCrunch, what do we care? StatCrunch is going to do all the work. Okay, so to come up with so we want to give an estimate of the standard deviation of the population. That's what that sigma symbol is. And so, big picture, when you're estimating the standard deviation of the population, you use a chi-square distribution or a variance distribution. If you're doing the proportion, you use p-stat calculator. If you're using the mean, you do either the z-stats or the t-stats, depending on if you know sigma for the population. Here's our little list here, actually. So we have z-stats, t-stats, proportion stats, but when we're looking for sigma, we use variance stats. And we have one sample. Two samples will be what we start in Chapter 9. And in this case, we have the data instead of a summary. We actually have the data. So then I select the column. Just change this box size a little bit. I would select the column where my data is, which all in variable 1 column, so I would select that. And then, as I mentioned before, we have a couple of options to perform. We can do a hypothesis test. That will be in Chapter 8, next chapter. We're almost there. And then for the confidence interval, we would select that. But notice it says confidence interval for sigma squared. So that means what StatCrunch is doing is using the variance and doing things about variance, and the chi-square distribution is about variance. And in the end, we're going to have to give a confidence interval about the actual standard deviation, not the variance. All right, nonetheless, we still want a confidence interval of 90%, so I'll change the default from 95 over to 90%. So I just picked the column, I selected confidence interval, and I put in the level of confidence I want, and I hit compute. And I get the box very similar to what we got for the proportion and mean estimates. And it says variable 1, and it has the degrees of freedom is 11, because there were 12 pieces of data, as we can see in our little list here, and it gives a lower and upper limit for our confidence level. But we have to be careful here. These lower and upper limits are for the variance, because it says here this is a sigma squared, a variance of variable confidence interval. And so we need to do like I showed on the slide, where they took these upper and lower limits and they square root them in order to get the actual confidence interval for the standard deviation instead of the variance. So that's why I have my calculator open here. So I'm going to grab this left limit for the variance, drop it into my calculator, and hit the square root. And I get this big number, and they want this rounded to 1 decimal place, so that looks like 3.3 if I round that to 1 decimal place. And then similarly, I'm going to square root the upper limit value, because that's for variance. Drop it in the calculator, square root it. And then I'm going to have 6.8 when rounded to 1 decimal place. 6.8. So be careful. You might be tempted to just grab these numbers and drop them in here, but because these numbers are for variance and they want the confidence interval for standard deviation, you have to square root the StatCrunch results to get the variance. I'm sorry, get the variance in terms of standard deviation. Okay, and might as well finish up this problem. So it says, does the confidence interval describe the standard deviation of all times during the week? Choose the correct answer below. So if we read back through the problem, it says they were obtained only at 3:30 on a Wednesday. It was simple random sample because it's just whatever cars went by there, but it was at that specific time. So I would say no, it's not for all times of the week. And let's see if their answer makes sense. The confidence interval estimate of standard deviation of population of speeds at 3:30 on Wednesday, not other times. Okay, so hopefully that gives you an idea of how, when working with confidence intervals for standard deviation, things are for the most part the same as the earlier work we did in the first two sections, but there are some significant differences you need to be aware of. And you want to get used to this look of the chi-squared distribution that's a little bit right skewed. We're going to be using that again later for some other work we do. We're going to return to this chi-squared distribution for other things as well. But hopefully that'll get you what you need to know to finish up this chapter well. So keep up the hard work, and I'll see you when I see you.